All right, 3.2 graphs of functions. A graph can be used to define a function or a relation. If the point xy is on the graph of f, then y is the output produced by the input x. I don't know why there's a space there. That's just bad English. Or y is equal to the function of x. Y equals f of x. Example 1, a function defined by a graph. The graph in the figure defines the function f. Determine the following: f of 0, f of 3, the domain of f, and the range of f. So if we're looking for f of 0, that means that we plug in when x is equal to 0. So basically what this is asking for is when x is 0, what is y going to be equal to? If I look at my graph, when x is 0, y is 7. I can tell that because, well, that's where it crosses, right there. So that would be 7. What about f of 3? So I go over to 3, and y is equal to 0. When it asks for the domain of f, that's all of the values of x that work for this function. You'll notice that I have this point here, which is solid, which means it includes this point. So from -8, it's going to be a bracket because it includes the point -8. And then it comes all the way up here to when x is equal to 2. But you see that it's a open circle. So because that's an open circle on both of those, it says that it does not include the point 2. So it stops at 2. And it's a parenthesis because it's an open circle. And then it picks back up at 2. So it goes from 2 and another parenthesis because this is an open circle up until we hit 7, sorry, and stops there. And that's a closed circle, so you get a bracket. Now our range is looking at all the y values across this interval. So for our y values, there's no y value that's not included. Like even here, this point here is not included, but it is included over on this piece. So when we're looking at the range, it's all of the values from the bottom to the top, especially in this case because they're all included somewhere else. As we discussed this one, if I look at where this open circle is, that point when y is 6 is contained over here. So our range would just be going from -9 to 8. Enclosed circle for both of those. So it's a closed bracket. All right, let's zoom in on this. So we have the vertical line test. A graph in a coordinate plane represents a function if and only if no vertical line intersects the graph more than once. So the vertical line test says that when we draw a vertical line, it cannot hit the graph more than once. That's how we decide that it's a function. Example 2, determine whether a graph defines a function. Well, here if I draw a vertical line in, at any one of these points, if I was to draw a vertical line in here, that's supposed to be vertical. Let's see if we can make it. Yeah, we have to zoom back out in order to make it work. But in order to create a vertical line here, straight up and down. Now when I draw that, it goes through two separate points. It goes through the point here and the point here. So this would not be a function. Moving on to the next one. If I draw a vertical line, at any point, it can never go through more than once. This one goes through here, but nowhere else. If I just kept drawing vertical lines, you would see that would always be the case. It's not going to go through the red line more than once, or the graph of our function more than once. So this one would be a function. So vertical line test is an easy way to determine whether or not it would be a function. Next, we have analyzing graphs and functions. So when we look at analyzing graphs for increasing and decreasing functions, a function is said to be increasing on an interval if its graph always rises as you move from left to right. Important that you're always going to move from the left to the right. It is decreasing on an interval if it always falls as you move from left to right over the interval. A function is said to be constant on an interval if it is a horizontal line over the interval. So if we're looking at each one of these and whether they are increasing, decreasing, and constant, if I look at this first one, as I start from the left and I move towards the right, it is always going up. There are times where it's going up less, but it continues going up and never drops back down or stays the same at any point. Always rising, so this would be increasing across this entire interval. The second one would be decreasing because it starts here, and as I go from left to right, it's always dropping. And obviously the last one is a horizontal line, so it is constant over the interval. Example 3, when a function is increasing and decreasing. On what interval is the function f of x equals absolute value of x plus the absolute value of x minus 2, increasing, decreasing, or constant? So for this one, I'm just going to go to Desmos and I'm going to graph this. I can do absolute value of x plus absolute value of x minus 2. And I need to know what intervals it's increasing, decreasing, and constant. Well, if I look at this graph, and I can go as far as I want, but from negative infinity all the way to 0, this is constantly decreasing. As I work from left to right, it's constantly going down. So this is decreasing. From negative infinity to 0. Now if I go from here to here, it's staying the same. So this would be constant from 0 to 2. Would help if I could spell. And lastly, it would be increasing from 2 to infinity. Just looking at starting at 2, it goes up as we go from left to right. So that's all there is to looking at a graph and telling whether it's increasing, decreasing, and constant, and on what intervals it's occurring. All right, local max and min. The graph of a function may include some peaks and valleys. A peak may not be the highest point in the graph, but it's the highest point in its neighborhood. Similarly, a valley is the lowest point in its neighborhood. Sorry, I might have just bumped my mic there. Um, so if you think about just in Aliquippa, I mean, if we are looking at the highest point in Aliquippa, that's clearly not the highest point on Earth. So it's a local maximum, but it's not the max. Same thing with the valley. It's the lowest point in the neighborhood, but it's not the lowest point on Earth. The lowest point in Aliquippa is not the lowest point on Earth. So it shows that it's a local minimum. The function f has a local maximum, x equals c, if the graph has a peak at the point c and f of c. So whenever I put c into the function, if the y that comes out is the highest point, then that is going to be a local maximum. So for every point x then that is around c, its y will be lower than at this point. So no y's around it will be higher than that point. A function also has a local minimum at x equals d if the graph of f has a valley at d and f of d. So all the points around that one have to be higher. And that's a good stopping point for today. We'll pick up there tomorrow and finish out learning about local maxes and mins and look at more analysis of functions.